This video is Kinetics4. And first we'll look at the half-lives for first, second, and third order reactions. Then we will look at a summary of everything so far regarding the rate laws and the half-lives. All right, we will start with first order. All three half-lives have the symbol T subscript 1/2. And the definition is the time it takes for the concentration to decrease to half of its original value. So let's say your solution starts out 2 molar, the reaction begins. What is the time it takes for the reactant concentration to drop to 1 molar, so to half of its initial value? That's kind of the basic concept there. All right, we will do a little bit of math here. So we will look at the integrated equation for first order. Natural log of A over A0 is equal to negative KT. And we're just going to kind of invoke the symbolism and the idea and insert it into this equation. So let me get my pointer here. When time equals T1/2, then concentration at that time will be equal to A initial over 2. Let me say it again. When T equals T1/2, then A will be equal to A initial divided by 2. So we can actually substitute that right in. Say this would be A initial divided by 2. And then this is A initial here. This is going to be equal to negative K times T1/2. So this equation has to be true if T equals T1/2. So then you can cancel the A0s. Rewrite it. Natural log 1/2 equals negative K T1/2, or the half-life. Then take this negative sign and move it over here. So negative ln 1/2 is equal to KT 1/2, the half-life. And then now this 1/2 is going to become the power here. So then if you have 1/2 to the negative 1, that's 1 over 1 over 2, which is 2. So then the next step is ln 2 is K times T1/2. Take the natural log of 2 in your calculator, push those buttons, and you get 0.693. Solve for T1/2, and that is equal to 0.693 divided by K. First order half-life. All right. Next, it would be an example and a graph of this. So let me scroll up here. Excuse me. And here is an example, which is, it's our same N2O5 reaction again. This time we're looking at the rate constant and T1/2. So the rate constant for decomposition of N205. And if you remember, this is a first order decay, first order rate law for the N205 decomposition, is 1.7 times 10 to the minus 3 seconds to the minus 1. So we figured that one out in the last video. And I didn't mention this before, but this is at 45 degrees C. You don't need that information, but if you change the temperature, the rate constant would change. So just forget about that. But anyway, okay, and then calculate the half-life. All right, so we say T1 half is equal to 0.693 divided by 1.7 times 10 to the minus 3 seconds to the minus 1. So 0.693 divided by K. Calculate that. T1 half is equal to 407 seconds. Now the units go 1 divided by 1 over seconds, so the seconds comes up into the numerator. And this is also 6.7 minutes if we wanted it in minutes instead. It's always practical in the lab to know how many minutes it's going to take for the concentration to drop by half. All right, so then the graph here is interesting. So if you go back to the data that we had earlier, the data in that table, I've been looking at this reaction for a while. Okay, so if you have 0, this is time in seconds. So you have 500, 1,000, and 1,500 and 2,000 seconds. Starting with 0.002. This is the concentration of N205. 4, 6, 8, 10, 12, 14, 16, something like that. So 004, 006, 008, 10, 12, sorry, and 016. All right, and let us say that we start with your initial concentration. This is the concentration we had in part of this problem earlier. So about up here somewhere, this is equal to 0.0165. That was given earlier. So let's start there. Let's just call it 0.016. All right, so then it's going to take 407 seconds for it to go from 0.016 to 0.008. Then you start with a 0.008. It's going to take another 407 seconds for it to drop to 0.004. So 407 plus 407 is 814. So that's going to be someone in here, 814. And now the concentration has dropped by half again. So it's gone from 0.008 down to 0.004. All right, then you got to add another 407. So what is that? So 814 plus 407, 11, 2, 12. Is that right? 12. Get that right? I think so. So 1221 will be someone in here. 1221. Let's get rid of that. And then that's taking the system from 0.004 molar down to 0.002. So it looks like that. You can see here it's first order, and that this is, oops. this is an exponentially decreasing function, as you would expect. Also, we saw that, there were 1, 2, 3 half-lives, and they all have the same value of 407 seconds. So all half-lives are 407 seconds for this example. And you can talk about, I don't really want to draw this here. So maybe on the bottom here. Let me do it in a different color. So from here to here, that's the first half-life. And then from here to here is the second half-life. Here to here is the third half-life. And if I was using graph paper, it would be clear that all these T1 halves are the same. But then this one is referred to as the first half-life. This is the second half-life, and that's the third half-life. When you do an experiment, you want to make sure you extend your data out up to fourth and fifth half-life so you get a good exponential curve there. You don't want to truncate it too quickly. You might even think it were linear if you did that, which it's absolutely not. All right, so then now we are going to look at second order half-life. Excuse me. Also given the symbol T1 half. And we start with the integrated rate law again. 1 over A is equal to KT plus 1 over A initial. And we're going to invoke that same idea that when T is equal to T1 half, then A will be equal to the initial concentration divided by 2. So we'll say 1 over A initial over 2 is equal to KT1 half plus 1 over the initial concentration. So left-hand side then would be 2 divided by A initial. So it's 1 over 2. So the 2 comes up into the numerator there. Let's subtract the 1 over A initial on the right-hand side. So it ends up on the left. And then this is K times T1 half. So 2 over A0 minus 1 over A0 will be equal to 1 over A initial, or A0. This is equal to K times T1 half. Solve for T1 half. And this will be 1 over K times the initial concentration. Second order half-life. All right, now for this one, we can look at a experiment as well. And this would be an example here. 2 NO2s. We've looked at this reaction before as well. 2 NO plus O2. K is equal to 0.775 molar to the -1 seconds to the -1. Notice the units here are consistent with it being a second order rate law. And let's see, the initial concentration is 0.0030 molar. So what is the half-life? All right, this is not too bad. It's just a plug into this equation. T1 half is equal to 1 over K times A initial. So we can grab the different parts here. 1 divided by k, which is 0.775. And use your units, please. Molar to the -1, second to the -1. And then 0.0030 molar for the initial concentration. Whoops. Notice that the molar to the -1 cancels with the molar. So we have 1 over seconds. So the seconds come up into the numerator. The units for the half-life should be seconds. All units for half-lives have to be in time. We start with seconds and then can switch them out if we need to do that. All right, so solve for that. And that is 430 seconds. Okay, now the graph of this one is different. So this is going to be concentration. I guess we could probably put here NO2 concentration versus time. Time frame here is up to 3,000, so 0, 500, 1,000, 1,500, 2,000, 2,500, 3,000, something like that. Seconds. Okay, and concentration here. Our initial concentration was 0.003. Half of that, 0.0015. Half of that, 0.00075. And one more time. Let's see, so it's going to be 0.000375, like that. Okay. All right, so the half-life is 430 seconds. And when the concentration is 0.003, that'll be 0 time. 430 seconds. I always mess this up, by the way. I probably will this time as well. So 430 seconds, it's dropped by half, so we get that. Then, if you look at the equation for half, wait a minute, I made a mistake. Oh, I'm sorry, that's okay. All right. So if here, for the second half-life, we're going to take the value of 0.0015 as the initial concentration, and then we're going to let that go to half as well. So if we're using 0.0015, we're going to say that the concentration here is A initial, and then we're going to let it drop to half of its value again. So what I'm saying here is that the initial concentration 0.003 we started out with here. Now we're going to take 0.003 and divide it by 2. So there's a factor of 2 that comes up into the numerator here. If you put in 0.003, it'll be 2 over that, which is it's your new initial concentration. So when that happens, when you calculate T1 half, you get a doubling effect. So the second half-life is twice the value of the first half-life. So then we have this T1 half for the first half-life is 430. The second half-life is going to be twice that, so it's 860. The third half-life is going to be twice the second half-life. So that's going to be, what is that, 0, 12, 17, like that. And then you have to add each one. So if this is 430 right here, then you have to add 430 and 860 together, 912. So the difference, the total amount will be 1290 in here somewhere. So this part right here, that difference will be 860. This difference is 430. The next one is, the difference is going to be between second half-life and third. You got to add an extra 1720 to it. So that's going to be 1103, is that right? That's a 0. Yeah, 3010. So the total amount will be 3010, way out here somewhere. And then the difference between them is 1720. That's complicated, right? Okay, so then we're expecting, let's see, we start with 0.003, let it drop by half, that's 430 seconds. For it to drop by half again, that's going to be an additional 860 seconds. For it to drop by half again, it's going to be an additional, to go from 0075 to 00375, it's additional 1720. And so the graph looks like this. This graph looks exponential. It looks like the first order decay, but it's not. There's no logarithm in this equation. There's no e in the equation. It is not an exponential decay. So instead, it's referred to as a hyperbolic curve, and there is an inverse relationship between the initial concentrate, or rather the value of K, and the half-life. So you remember from first semester, remember we had PV is equal to a constant, and if you graphed that, you got a curve that looked like this one. And we said P then is equal to a constant times 1 over V. And if we plotted it that way, then it would be a linear relationship. So that's the kind of curve this one is. It's called a hyperbolic curve. It is not exponential. All right, so then if you had similar initial concentrations and similar first half-lives, then if you superimpose the first and second order on the same graph, so this would be concentration versus time, you would see that the first order decay is exponential. It looks like this. Oops, I didn't mean to go that far. I'll leave it, straighten this out here. Yeah. Okay, so this would be first order. And then what we'd find is for second order decreases more steeply, and then because those half-lives get longer, it tends to drag this out for quite a bit longer until it finally comes down to the baseline. And so the second order graph looks like that. So then the lesson here is that when you are in the laboratory and you're doing your experiments, you are tabulating time and concentration, right? And so if you just plot concentration versus time, and let's say you get a graph that looks like this, okay, you've got maybe that's your experimental graph. You don't know if it's first order or second order because the graphs look pretty similar. You can't just jump to it and say, okay, it's exponential decay. It's not necessarily exponential decay. So you have to test for it to see if the data obeys first order kinetics or if the data obeys second order kinetics, and you need to look at the integrated rate laws for that. So you'd take your data, you'd plug it into your first order equation, the natural log of A over A0 is equal to negative KT, And actually, if you do the log plot on that one, if you do not get a linear relationship, then it's not first order. So if it's not first order, then try your second order equation. You're going to plug your data into 1 over a is equal to kt plus 1 over a0, and you want to see if you get a linear relationship there. If so, then it's second order. All right, one more to do. Sorry, that's my last slide there. That's my summary. Okay, so then before we end this, we have zero order. Half-life, and here the integrated equation A is equal to negative kt plus a initial, and we're going to use our same idea here that when t is equal to t1 half, then a is equal to a initial over 2. And you can solve here, you can play around with that and solve for it. It'll be t1 half is equal to a initial divided by 2k. So I am actually not going to worry too much about this one. I've just given it to you for completion. The plug-in problems for zero order are very, very easy. I'm not going to bother with an example here. Okay, so then on my next here, whoops, no slide, I typed up this stuff for you. And let's just shrink it down a little bit. If I can, there we go. And this is a good summary. There's a summary in your book, but I didn't like it so much. I had a summary from Tro, which I used at Cal State Northridge. I didn't like that either, so I just made up my own here. And hopefully there's no typos, because I just did it. So here's the integrated equation for zero order. This is the integrated equation for first order, and if you take e to both sides and then use the relationship between natural log and log, this is the equation for first order. That's the integrated equation as well, but you would use this for graphing. And then, but this one you just solve problems the way I showed you in the last video. This one is second order, and here you're plotting 1 over a versus t. You want to see if you get a linear relationship. Here it's a versus t, and over here it's log of a versus t. So there'd be different graphs that you would do. The units have a pattern, molar times seconds to the -1 for 0. You could say molar to the 0 power here times seconds to the -1, and here's molar to the -1 times seconds to the -1. So seconds to the -1 stays the same. You get molar to the power 1, molar to the power 0, and molar to the -1. All right, the half-lives we just did. Half-life for zero order, first order, and second order. We need the initial concentrations for 0 and second order. All right, now I just want to show you the graphs as well. I don't know if I can fit all this here, but if it's, maybe I'll have to do it this way. So if it's a first order situation, you would plot, I have to make this small because there's a bunch that I want to show you here. A versus t. It's got a negative slope there, and so it's going to be linear with a negative slope. Then you have that, and also there's one more. I'm going to write this one twice. You'll see why. And then there's one more here. If we say the rate is equal to k times a to the 0 power, because a is 0, rate is equal to k, the graph of the rate versus concentration is constant. It's just k, right? Because this part goes to 1. So rate is a constant on that one. So here, if it's first order, and you plot A versus T, you're going to get that exponential decay, right? So this is A is equal to A initial e to the minus kt. Then on this one, if you use ln A, or you could use base 10 log, is equal to negative kt plus the natural log of A 0. So this is actually how you test for first order. This particular graph I'm going to show you here, which is very tiny, you'll have the log of A versus T. It's got a negative slope, so this one will be linear with a slope equal to negative k. Negative k. That's the test, that one. That's an E right there. Slope. And then finally, if you plotted rate versus concentration, you get a linear relationship. So it's very different, right, from zero order. Now for second order, if you plot A versus T, you get that second order curve. Looks like exponential, but it kind of drags out longer to get to 0. Still not at 0, but okay. And then you don't know if it's first or second, so in the next step, you would say, okay, I have to plot the integrated rate law. 1 over A is equal to kt plus 1 over A initial. So this is going to be, hold on, let me erase here. Not going to let me do that. Oh, here we go. A little bit more space there. So that graph will be 1 over A versus T. It's got a positive slope. It's got an intercept as well. So this would be, the K is the slope. All right, so then this is an important connection here. Let me give it to you one more time. If you graph your data A versus T, you cannot jump to the conclusion that it's exponential. You don't know if it's first order or second order. So you've got to go to the next step. The next step is to use the integrated rate law. If you plot log A versus T and it's linear, then you know it's first order. But if it's not linear, then you use the second order integrated equation, 1 over A versus T. If that's linear, then you know it's second order, right? And vice versa. And then one more thing here, rate versus concentration. And that one, because it's squared, right? So you got rate is equal to K times A squared. You're going to get a parabola. This one here is rate is equal to K times A to the first power. So that's linear. But this last one, you got a parabola. All right, that is a lot to digest, but I think this final slide here summarizes things for you. You'll find tables similar and graphs similar and figures similar in your book that are a little bit bigger than that, easier to look at, but hopefully you got some background there. We'll stop. Thanks.